Assistant Professor in Andhra Pradesh State University's Electronics and Communication Engineering 2018 Question Paper Solutions Part 5, that is from question number 121 to question number 150. Question number 121. A system has a transfer function g of s is equal to 1 by s plus 12. This is a transfer function given. So for this transfer function we need to find the settling time and rise time. The standard form of first order control system is k by 1 plus s2, where tau is the time constant, and for this standard first order control system settling time is given as 4 tau. Settling time is equal to 4 tau for 2% tolerance band. So compare the given transfer function 1 by s plus 12 with k by 1 plus s tau. Take 12 as common, 1 by 12 in the numerator, 1 plus s by 12. Now the time constant tau is equal to 1 by 12 second. So from this settling time ts is equal to 4 tau 4 into 1 by 12, that is 1 by 3 second, or 0.33 seconds. Settling time is 0.33 seconds, and they also ask you to calculate the rise time for the first order control system. So rise time is defined as the time taken. The definition of rise time is the time taken for the response to rise from 10% to 90% of its final value for unit step input. And for first order control system, for step input for first order system, rise time is given as 2.2 tau. Rise time is equal to 2.2 into tau. So we know that tau is 1 by 12 seconds. So that is 2.2 into 1 by 12 seconds. On calculation, its value is 0.183 seconds. Therefore, rise time is 0.183 and settling time is 0.33 seconds. Correct option is option 1. Next question. Given a system with transfer function g of s is equal to 10 by s square plus 10, the system response is. So given transfer function g of s is s square 10 by s square plus 10. So the denominator of transfer function is characteristic equation. So from this characteristic equation is s square plus 10 is equal to 0. This is a characteristic equation. So compare this characteristic equation with standard second order system characteristic equation, that is s square plus 2 zeta omega n s plus omega n square is equal to 0. Here the value of omega n square is 10. From this omega n is root to 10 radian per second, and 2 zeta omega n, its value is 0 because the coefficient of s power 1 is 0 in the given characteristic equation. So from this omega n is root to 10 into zeta is 0. So from this zeta value is 0. Hence the nature of, if damping ratio zeta is 0, then the nature of system is undamped. The nature of system is undamped. Correct option is option 3. Next question. A system has two poles at s is equal to minus 5. At s is equal to minus 5, there exists a repeated pole. What is the value of damping ratio? From this, the characteristic equation is s plus 5 whole square is equal to 0. That is s square plus 10s plus 25 is equal to 0. Compare this characteristic equation with standard second order system characteristic equation, s square plus 2 zeta omega ns plus omega n square is equal to 0. So from this, omega n square is 25, omega n is 5 radian per second. Natural frequency is omega n refers to natural frequency. Then 2 zeta omega n, its value is 10. 2 zeta omega n value is 10. Coefficient of s power 1, that is 2 into zeta omega n is 5 is equal to 10. From this zeta is equal to 1. If zeta is 1, the nature of system is critically damped. If the poles of system or roots of characteristic equation are real and equal, then nature of system is critically damped. Zeta is equal to 1. Here the correct answer is option 2. Next question. The settling time of a second order system whose transfer function has exactly 2 poles at minus 3 root 3. So as seen from the previous question, poles are real and equal. Therefore, it is a critically damped system. Zeta is 1. The characteristic equation is given as s plus 3 root 3 whole square is equal to 0. From this, s square plus 6 root 3s plus 3 root 3 whole square is equal to 0. Compare the given characteristic equation with standard second order system characteristic equation s square plus 2 zeta omega ns plus omega n square is equal to 0. So from this, omega n is 3 root 3. This is omega n square omega n. Omega n is the value of omega n is 3 root 3 and zeta 2 zeta omega n is equal to 6 root 3. Zeta omega n is 3 root 3. So we know poles are repeated. Poles are real and equal. Poles are repeated. Critically damped system. Zeta is equal to 1. That is 4 by zeta is 1. Omega n is 3 root 3. 4 by 3 root 3. Its value is 0.77. Settling time 0.77 seconds for 2% tolerance band. Correct answer is option 2. Next question. Question number 125. Given closed loop transfer function T of s is equal to 10 by s power 5 plus 2s power 4 plus 3s cube plus 6x s square plus 5s plus 3. The denominator of closed loop transfer function will give characteristic equation. From this characteristic equation is s power 5 plus 2s power 4 plus 3s cube plus 6x square plus 5s plus 3 is equal to 0. This is a characteristic equation for a given closed loop transfer function. Now we need to calculate how many poles of the system have on the right hand side of the S plane. So to calculate the number of poles on right hand side of S plane, we need to use RH criteria, Routh-Hurwitz criteria. So from this, write the coefficient s power 5, s power 4, s cube, s square, s power 1, s power 0, and the coefficient of all terms are 1, 3, 5 here. That is 1, 3, 5, and the coefficients of even powers 2, 6, 3. And then do cross multiplication. 2 3s are 6, 6 1 is 6, that is 0, and then 2 5s are 10, 10 minus 3 by 2, 2 5s are 10, 10 minus 3 7, 7 divided by 2, that is 3.5, 7 by 2 is 3.5. Now 0 came in the first element, replace it as small number epsilon. Then 6 epsilon minus 7 by epsilon. Next element is 3. Epsilon into 3 by epsilon, that is 3. Next element, the coefficient of s power 1. The coefficient of s power 1 is minus 3 epsilon or 6 epsilon minus 7 by epsilon into 3.5 minus 3 epsilon divided by 6 epsilon minus 7 by epsilon. Next, coefficient of s power 0, it is 3. Now we need to check the number of sign changes. Replace epsilon with 0 here. Replace epsilon with 0 in the first column. Then we will get minus 7 by some small number. Here it is negative. The element is positive in the first column. Positive. Here it is positive. Negative. Replace 0 here. It will be 0. 0 minus 7 into 3.5 minus 21 around minus 20s by small number. It is also a negative number. It is also negative number. Then it is plus 3. So number of sign changes in the first column are, here it is one sign change. Negative to negative there is no sign change. From negative to positive there are two sign changes. Two sign changes in the first column of Routh array. Hence two poles exist on the right hand side of S plane. So correct answer is option 3. Next question. For a unity feedback system with forward transfer function g of s is equal to k into s plus 20 by s into s plus 2 s plus 3. This is a forward path transfer function, and feedback path transfer function h of s is 1. So from this characteristic equation is 1 plus g of s h of s is equal to 0. So that is 1 plus, write g of s as this expression, k into s plus 20 by s into s plus 2 s plus 3, and h of s is 1. Rearrange the expression, we will get characteristic equation as s cube plus 5s square plus 6s plus ks plus 20. That is s cube 5s square plus s into 6 plus k plus constant term 20k is equal to 0. So for this characteristic equation, apply RH criteria to find the k value. By using RH criteria, arrange first s cube, s square, s power 0 and s power 1 and s power 0. Arrange the coefficients r to power 1, 6 plus k, and then 5, 20k. So go with the cross multiplication. 20k minus 6 5s are 30 minus 20k plus 6 5s are 30 plus 5k by 5, and the coefficient of s power 0 last element is, here it is 20k. For the system to be stable, there should not be any sign change in the first column of Routh array. Hence, for the system to be stable, all the coefficients in the first column of Routh array should be positive sign or of same sign. Sign of all coefficients in the first column should be same. All are positive sign or all are negative sign. Therefore, 20k should be greater than 0. So k greater than 0. This is one condition. Next condition is 30 plus 5k minus 20k divided by 5 should be greater than 0. 30 minus 15k greater than 0. That is 30 greater than 15k. 15k less than 30. K less than 2. K greater than 0. K should be greater than 0 and the value of k should be less than 2. The range of k for the system to be stable is 0 less than k less than 2. Correct answer is option 1, 0 less than k less than 2. Question number 127. Given a matrix A is equal to 211, 171, minus 3, 4 and minus 5. These are the elements of matrix. The number of poles in left half of the S plane. So the poles are nothing but eigenvalues of the system matrix. To calculate the eigenvalues, we need to take A minus lambda I is equal to 0, where I is the identity matrix, A is the given system matrix. On calculation, we will have lambda is plus 7.495 minus 4.88 plus 1.392. Here there is only one pole in the left half of the S plane and two poles in the right half of the S plane. So correct answer is option 1. The number of poles in left half of S plane is only one pole, minus 4.88, and the pole is at S is equal to minus 4.88. Question number 128. Unity feedback system has the following forward transfer function. G of S is equal to 10 into S plus 20 S plus 30 divided by S into S plus 25 S plus 35. Also given feedback path system is unity feedback. H of S is equal to 1 and input is 15 T U of T, that is ramp input. For a ramp input, they ask to calculate the steady state error. We know that for a ramp input, steady state error is given as ESS is equal to A by kV, where kV is velocity error constant, limit s tends to 0, S into G of S H of S. kV is equal to, first we will calculate kV, limit s tends to 0, S into G of S. So this is G of S and H of S is 1. So on keep this SS get cancelled and substitute S is equal to 0, we will have 10 into 0 plus 20, 0 plus 30, 0 plus 25, 0 plus 35. Its value is 48 by 7. So the steady state error ESS is equal to A by kV, where 15 is the amplitude of the signal. Given ramp signal amplitude is 15. So that is 15 divided by 48 divided by 7. That is 15 into 7 by 48. So its value is 2.1875. Correct answer is option 4. Next question. A closed loop system is given. Maximum overshoot for unit step response is 25% is given. On peak time is 2 seconds and the value of J is 1 kg meter square. We need to calculate the value of undamped natural frequency. The question is we need to calculate omega n, undamped natural frequency. This is a inner loop. On solving this inner loop, we will get this expression k by js 1 plus k by js into k. The overall transfer function for this inner loop is this one. Next, again it will form a loop here, one closed loop. These two elements are in seriously connected, cascaded product of the transfer functions. It will form a single element like this, and again it is a closed loop transfer function. From this C of S by R of S, this is the final expression. Also in the question they have given maximum overshoot for unit step response is 25%. So maximum overshoot is e power minus pi zeta by square root of 1 minus zeta square into 100 is 25%, that is 0.25. From this zeta value, damping ratio zeta is 0.404 and peak time is 2 seconds. 2 seconds peak time is given, that is pi by omega n square root of 1 minus zeta square 0.404 square is 2. From this omega n is 1.72 radian per second. 1.72 radian per second. Correct answer is option 2. Question number 130. Given transfer function g of s is equal to k by s into s plus 1 into s plus 2 and feedback transfer function h of s is equal to 1. So from this characteristic equation is 1 plus g of s h of s is equal to 0. So on calculation we will get the characteristic equation as s cube plus 3s square plus 2s plus k. We need to find the value of k value by using RH criteria. RH criteria, here all the elements in first column should be positive, k should be greater than 0, the coefficient of s power 1, that is 6 minus k by 3, 6 minus k by 3, k by 3 is equal to 0. Now k marginal is the value of k marginal is 6. Now auxiliary equation is 3s square plus 6 is equal to 0. 3s square plus k is equal to 0. This is the auxiliary equation which is obtained from this column. 3s square plus k will give auxiliary equation. S is equal to plus or minus 2j. It is a point of intersection with root locus. Therefore, gain corresponding to the points where root locus crosses the imaginary axis is k value is 6. Correct answer is option 4. Next question. Consider a control system is given below. The intersection of asymptotes on the real axis is. So we know that the point of intersection of asymptotes is centroid, and centroid always lie on the real axis. To calculate centroid, sum of real part of poles minus sum of real part of zeros divided by number of poles minus number of zeros. In the given transfer function, there are 3 poles and 1 0. So 3 poles and 1 0. Number of poles is 3. Number of zeros is 1. And the location of poles, real part of poles, for s square, here it is 0 0 0 plus 0 plus minus 3.6, it is 3.6. Minus 3.6 minus real part of zeros, that is minus 1. Minus 1 divided by number of poles. Number of poles are 3 and number of zeros are 1. That is minus 3.6 plus 1 divided by 2. 2.6 by 2 minus 2.6 by 2. The centroid is minus 1.3. Centroid exists at s is equal to minus 1.3 on the real axis. Correct answer is option 2. Next question. Given forward path transfer function g of s is equal to k by s plus 2, s plus 4, s plus 6. So open loop poles are at minus 2, minus 4 and minus 6. Minus 2, minus 4 and minus 6. Location of open loop poles. And feedback path transfer function h of s is equal to 1. Also given the value of k to yield 10% overshoot for unit step input is maximum peak overshoot is 10%, 0.1 e power minus pi zeta by square root of 1 minus zeta square is equal to 0.1, that is minus pi zeta by square root of 1 minus zeta square is equal to natural logarithm of 0.1. On calculation we will have zeta is equal to 0.59 n. Corresponding to the dominant pole location is S is equal to minus zeta omega n plus or minus j omega n square root of 1 minus zeta square. So arbitrarily or randomly choose omega n is equal to 4. We will have desired dominant complex conjugate pole is minus 2.364 plus or minus j 3.231. S1 and S2 are the dominant pole location. Now, so this is the dominant pole location. So for this dominant pole location, for the point to be in root locus, it must satisfy the angle criterion. Angle g of s is equal to minus 180 degrees. So the angle of open loop transfer function is at s is equal to dominant pole. From at s is equal to dominant pole, the compute the angle for the each pole. For s is equal to minus 2, angle is 96.5. For s is equal to minus 4, angle is 63.2. For s is equal to minus 6, angle is 41. Total angle is 180 degrees. Therefore point lie on the root locus. Now we need to compute the magnitude of k. Magnitude of k is equal to s plus 2, s plus 4, s plus 6. Magnitude, replace s is equal to minus 2.364 plus j 3.231. So on calculation we will get the product of these three values will give the value of k, it is 45.55. Therefore correct answer is 45.55, option 2. Next question, for a unity feedback system with g of s is equal to k by s plus 5, s plus 20, s plus 50, the 180 degree frequency is given. G of s is k by s plus 5, s plus 20, s plus 50 and h of s is 1. Phase crossover frequency omega pc. Omega pc, phase crossover frequency is the frequency at which phase angle of g of s h of s is minus 180 degrees. That is imaginary part of g of s h of s is equal to 0 at phase crossover frequency. At phase crossover frequency, imaginary part of g of s h of s is equal to 0 at omega is equal to phase crossover frequency. On calculation, angle g of j omega h of j omega is equal to minus 180. We know this formula, tan inverse a, tan inverse b, tan inverse c is equal to a plus b plus c minus abc by 1 minus ab plus bc minus ca. So apply the same formula here, then we will get abc omega by 5 plus omega by 20 plus omega by 50 minus abc, that is omega by 5, omega by 20, omega by 50 divided by 1 minus ab omega by 5, omega by 20 minus bc omega by 20 into omega by 50 plus ca omega by 50 into omega by 5 is equal to 0. On calculation we will have the omega value as 37, omega value as 37 radians per second. So correct answer is option 3. Next question, a closed loop bandwidth required for 20% overshoot and 2% settling time is. For second order system with unit step response, we have peak overshoot is e power minus pi zeta by square root of 1 minus zeta square, percentage is multiplied with 100. If it is percentage, multiply with 100. Next settling time is 3 by zeta omega n for 5% tolerance bond and 4 by zeta omega n for 2% tolerance. The bandwidth of second order system is given by omega n square root of 1 minus 2 zeta square plus under root 1 minus 2 zeta square whole square plus 1 and so on. So bandwidth in hertz. Now use this formula to solve the given question. Peak overshoot is e power minus pi zeta by square root of 1 minus zeta square is 0.2. Send this, remove this natural logarithm, remove this exponential, we will get natural logarithm of 0.2. On calculation, zeta value is 0.456 and settling time is 4 by zeta omega n. Four by zeta omega n. Given settling time is 2 seconds. So from this, zeta omega n is 2 and omega n is 2 by 0.456. It is 4.386 radian per second. Natural frequency is 4.386 radian per second. Substitute zeta and omega in bandwidth formula. First calculate 1 minus 2 zeta square. 1 minus 2 zeta value is 0.456 whole square, that is its value is 0.586. Now the bandwidth is omega n 4.386 under root 1 minus 2 zeta square. 1 minus 2 zeta square is 0.5861 plus under root 0.5861 whole square plus 1. On calculation, its value is 5.798. 5.798. It is approximately equal to 5.8 hertz. Bandwidth is 5 hertz. Correct answer is option 3. Next question. Steady state error can be made 0 by employing. So this integral controller is used to decrease the steady state error by increasing the type of the system. Similarly, derivative controller increases the stability of system without affecting the steady state error. Correct answer is option 2. Integral controller is used to decrease the steady state error. Steady state error can be made 0 by using integral controller. Next question. Question number 136. So this question is related to signal flow graph. Before solving this question, let us see the formula for let us see Mason's gain formula. So to calculate the overall gain for the given signal flow graph. So overall gain is equal to transfer function is equal to sigma pk delta k by delta, where pk is path gain of kth forward path, delta k is the value of delta obtained by removing all the loops touching the kth forward path. Delta is 1 minus sum of loop gains of individual loops plus sum of gain products of all possible combinations of two non-touching loops minus sum of gain products of all possible combinations of three non-touching loops. This is Mason's gain formula to calculate the transfer function of signal flow graph. Now, this given signal flow graph, RFS is the input and C of S is the output. It has two forward paths. This is one forward path and next forward path is this one. And two loops exist. This is one loop and this is a second loop. Only two forward paths and two loops and no non-touching loop exists. And there is no non-touching loop. RFS is input, C of S is output, path P1, forward path P2. So apply Mason's gain formula for path P1. Overall gain is 1 into 1 by s into 1 by s into 3, that is 3 by s square. For path P1, corresponding delta 1 is 1 because the value of delta obtained by removing all the loops touching the kth forward path. So remove the loops touching the kth forward path, remove this loop and this loop. So there is no loop. Delta 1 is 1. Similarly, path gain P2 is 1 into 1 by s into 1. Its gain is 1 by s. The value of delta 2 is 1. Now delta 1 minus loop gain of individual paths. So loop gain of this individual path is minus 10 by s. Loop gain of second path, second closed loop is minus 24 by s square plus product of two non-touching loops. There is no non-touching loop. Its value is 0. Now its value is 1 plus 10 by s 1 plus 10 by s plus 24 by s square. Now transfer function is P1 delta 1. P1 is 3 by s square, delta 1 is 1 plus P2 delta 2, 1 by s into delta 2 is 1, P2 delta 2 divided by delta 1 plus 10 by s plus 24 by s square. So rearrange this, we will have s plus 3 divided by s square plus 10s plus 24. This is the transfer function for the given signal flow graph. Correct answer is option 1. Question number 137. Einstein-Wiener-Kinchy relation of power spectral density is. We know that autocorrelation and power spectral density form a Fourier transform pair. Autocorrelation and power spectral density form a Fourier transform pair, that is Fourier transform of autocorrelation is power spectral density, that is integral minus infinity to infinity Rx of tau e power minus j 2 pi f tau d tau is Fourier transform of autocorrelation, which is a power spectral density. Similarly, autocorrelation function is obtained by taking inverse Fourier transform of power spectral density. The correct answer is option 1. Sx of f is equal to power spectral density is equal to integral infinity to infinity autocorrelation function Rx of tau e power minus j 2 pi f tau d tau, and autocorrelation function Rx of tau is equal to inverse Laplace transform of power spectral density. Correct answer is option 1. Next question. Autocorrelation function of power spectral density for a white noise is. So this is a power spectral density of white noise. Power spectral density of white noise whose magnitude is n0 by 2. This its Fourier transform is n0 by 2 delta of t. Autocorrelation function of white noise. This is a graph for autocorrelation function of white noise, graph for power spectral density of white noise. Therefore, Rx of tau is equal to n0 by 2 delta of t. Autocorrelation function is Rx of tau is equal to n0 by 2 delta of t. Correct answer is option 2. Next question. For a question number 139, for the zero modulated signal, quadrature null effect will take place when phi is equal to, obviously it is plus or minus 90. When phi value is plus or minus 90 degrees, then quadrature null effect will takes place. Let us see the derivation for this. In the demodulation of conventional amplitude modulated signal using synchronous detector, the output signal to noise ratio gets decreased due to non-zero local oscillator phase shift. Due to non-zero local oscillator phase shift, output signal to noise ratio decreases. The output signal to noise ratio due to non-zero local oscillator phase shift is signal to noise ratio at the output dash is equal to signal to noise ratio at the output into cos square phi. This is the ideal value. Due to non-local oscillator phase shift, this is the practical value multiplied with cos square phi. Signal to noise ratio of the output into cos square phi. When phi is plus or minus 90 degrees, signal to noise ratio of the output is 0. That is, demodulation is not possible. This is called quadrature null effect. Similarly, in demodulation of DSB-SC signal using synchronous detector, the output signal to noise ratio decreases due to phase shift in local oscillator. As phi value increases, output signal to noise ratio decreases. For phi is equal to 90, demodulation is not possible. It is a quadrature null effect. So no quadrature null effect will take place in SSB modulation. In conventional amplitude modulation, DSB-SC modulation, quadrature null effect takes place if local oscillator phase shift is plus or minus 90 degrees. This is a conclusion point. Correct answer is option 3. Next question. What is the other name for quadrature carrier multiplexing? Quadrature carrier multiplexing or quadrature amplitude modulation. This scheme enables two DSB-SC modulating waves resulting from two independent message signals to occupy the same transmission bandwidth, and yet it allows for separation of two message signals at the receiver output. This quadrature carrier multiplexing is bandwidth conservation scheme. Here two DSB-SC signals, DSB-SC1, DSB-SC2. Two DSB-SC signals are independently modulated and then quadrature multiplexed, which results simultaneous transmission of both signals and allows the separation of two message signals at the receiver output. Quadrature carrier multiplexing. The other name is quadrature amplitude modulation scheme. Correct answer is option 1. QPSK stands for quadrature phase shift keying. Question number 141. In DSB-SC modulation, the detector is in DSB-SC modulation in phase detection. The detector in upper path is referred as in phase coherent detector or I channel, and the detector in lower path is referred as coherent detector or quadrature phase coherent detector or Q channel. It is in phase coherent detection. So upper path, this is upper channel, here it is in phase coherent detector, and this is the lower channel or lower path referred to as quadrature phase coherent detector or Q channel. This is Costas receiver for demodulation of DSB-SC signal. Costas receiver for demodulating the DSB-SC signal. Correct answer is option 4. It is not out of phase. It is in phase coherent. It is not non-coherent. In phase coherent detection. Question number 142. If we subtract conventional AM with narrowband FM signal, what is the resultant signal? So let us see the time domain equation of conventional amplitude modulated signal for a single tone message signal. Time domain equation: AC into 1 plus mu cos 2 pi FMT into AC cos 2 pi FCT. On rearranging, S of t is AC cos 2 pi FCT plus AC by 2 cos 2 pi FC plus FMT plus AC mu by 2 cos 2 pi FC minus FM into t. This is the standard time domain equation for single tone message signal for conventional AM. This is expression 1. Similarly, the time domain equation of narrow band frequency modulated signal is, let it be S dash of t, AC cos 2 pi fct plus AC beta by 2 cos 2 pi fc plus fm into t minus AC beta by 2 cos 2 pi fc minus fm into t. Now let us assume beta is same as mu. Beta is modulation index in frequency modulation. Mu is a modulation index in amplitude modulation. Now these two terms AC cos 2 pi fct, AC cos 2 pi fct, AC mu by 2 cos 2 pi fc plus fm into t, AC cos 2 pi fc plus fm into AC beta by 2 cos 2 pi fc plus fm into t. These two terms get subtracted because in the question subtraction is given. Now resultant signal is only these two terms exist. That is 2AC mu by 2 cos 2 pi fc minus fm into t. It represents SSBSE signal, lower sideband without carrier. It represents SSBSE signal without carrier. If we subtract conventional amplitude modulation signal with narrowband FM signal where both modulation indices are same, then it results SSBSE signal, single sideband suppressor carrier signal. Next, question number 143. Arrange the correct order of super heterodyne receiver. So in super heterodyne receiver, the first section is receiving antenna, RF amplifier, mixer is here. Mixer is supplied with local oscillator signal, and then IF amplifier, demodulator, audio frequency amplifier, power amplifier, and loudspeaker. The correct sequence of blocks in super heterodyne receiver are RF section, mixer and local oscillator, IF section, and then amplifier, audio amplifier. RF section, mixer and local oscillator, IF amplifier, and then audio frequency amplifier. Correct answer is option 1. Question number 144. Which of the following option is used to select the desired signal in communication? So carrier frequency filtering or carrier frequency tuning is used to select the desired signal in communication. The process of varying local oscillator frequency to maintain constant intermediate frequency is called tuning. This is the definition for tuning. Tuning is performed at the receiver to select desired radio frequency signals. Now, the correct answer is carrier frequency filtering and carrier frequency tuning. Both are same. Correct answer is option 1 and 4. Next, the signal to noise ratio of DSPSC modulation system is represented by the channel signal to noise ratio. Channel signal to noise ratio of DSPSC system, that is signal to noise ratio of channel in case of DSPSC modulation is C square AC square P by 2 omega N naught. So this is same as signal to noise ratio or the output for DSPSC modulation. Therefore, frequency figure of merit for DSPSC is 1 because output signal to noise ratio same as channel signal to noise ratio. Figure of merit for DSPSC is 1. So correct answer is option 3, C square AC square P by 2 omega N naught. Next question number 146. Write the relationship between modulation index beta and bandwidth omega in a single tone modulation. The ratio of frequency deviation delta f to modulation frequency fm is called modulation index in FM wave. Beta is equal to delta f by fm, where delta f is kf into am. Kf is frequency sensitivity, am is amplitude of message signal, fm is a frequency of message signal. Correct answer is option 1. Beta is equal to delta f by fm. Bandwidth of FM signal using Carson's rule is bandwidth is 2 delta f plus fm. Bandwidth is 2 delta f plus fm. We know that beta is equal to delta f by fm. It can be written as 2 into beta plus 1 fm or 2 delta f 1 by 1 plus beta. Different formulas for bandwidth using Carson's rule for wideband frequency modulated signal, that is 2 into beta plus 1 fm, where beta is delta f by fm. Correct answer option 3. Next question, question number 148. A band limited signal is sampled at Nyquist rate. The signal is then recovered by passing it through. If any signal is sampled at Nyquist rate, then the signal can be recovered by passing it through an ideal low pass filter. So let us see three different cases. If a band limited signal is sampled at Nyquist rate, if it is sampled at Nyquist rate, then only ideal low pass filter should be used for reconstructing, because practical low pass filter has some extra frequency components which causes distortion. If it is sampled at Nyquist rate, then only ideal low pass filter should be used. That is sampling rate Fs is equal to 2 Fm. Critical sampling. If band limited signal is oversampled, if signal is oversampled, then practical low pass filter can be used. Practical low pass filter can be used. That is sampling frequency greater than 2 Fm. Similarly, if band limited signal is undersampled, if it is undersampled with the loss of message signal, then loss of message signal is irrecoverable, and even with ideal low pass filter it is not possible to reconstruct the signal. This is undersampling, where sampling frequency less than 2 Fm, less than the Nyquist rate or less than critical sampling. Loss of signal is irrecoverable, and we cannot recover the signal even if you go with the ideal low pass filter, and this method of sampling is not preferred. Three categories of sampling: critical sampling, oversampling, undersampling. Undersampling is not preferred. Ideal sampling is preferred. Nyquist rate is critical sampling is preferred. Critical sampling. Sampling frequency is 2 times of message signal frequency. Critical sampling is preferred if we have ideal low pass filters, but the design of ideal low pass filter is practically impossible. Hence, we will choose only oversampling so that we can use practical low pass filters. In the question, they have given Nyquist rate, sampled with Nyquist rate, that is critical sampling. The signal can be recovered by passing it through a ideal low pass filter. Question number 149. A 10 kHz signal is flat top sampled at the rate of 1800 samples per second. Sampling frequency is 1800 samples, and the samples are applied to a ideal low pass filter with cutoff frequency. The cutoff frequency of ideal low pass filter is 1100 Hz. The message signal frequency is 1 kHz. Now, the output of the filter contains which frequency components? We know that the frequency components present at the output are NFS plus FM. For n is equal to 0, it is FM, frequency component, message signal component 1000 Hz. Message signal frequency is 1000 Hz. Given message signal frequency is 1000 Hz. Next, cutoff frequency of ideal low pass filter is 1100 Hz, and sampling rate is 1800 samples per second. Nyquist rate is, we know that Nyquist rate is 2 Fm. The formula for Nyquist rate is 2 Fm, 2000 samples per second. This Nyquist rate is greater than given sampling rate. Therefore, the message signal is undersampled. We need to notice that message signal is undersampled. Now, frequency components for n is equal to 1, Fs plus Fm, Fs minus Fm. For n is equal to 1, frequency components are Fs plus Fm, Fs minus Fm. That is 2800 Hz plus 800 Hz. For n is equal to 2, 2Fs plus Fm, 6Fm, 2Fs minus Fm. It is 4600, 2600 and so on. For n is equal to 3 also. For n is equal to 0. Now, which frequency components are allowed by this ideal low pass filter having the cutoff frequency of 1100 Hz? The frequency components are 800 Hz and 1000 Hz. This is 800, 1000, 2800 is beyond cutoff frequency. 4600, 2600, all are above beyond cutoff frequency. The frequency components that are allowed are 800 and 1000. 800 and 1000 hertz components are allowed by the ideal low pass filter. Question number 150. In a PCM system with uniform quantization, increasing the number of bits from 8 to 9, increasing the number of bits from 8 to 9. So one bit is added. So and then reduction in the quantization noise power. In PCM system with uniform quantization, increasing the number of bits from n to n plus 1 will increase the signal to quantization noise ratio by a factor of 6 dB or 4. Hence, quantization noise power will increase by a factor of 6 dB, or otherwise its numerical equivalent is 4. Correct answer is option